Our last two examples will ask us to do a little bit more work to generate our results, but in the end the interpretations will be identical. So we're told in example 4 that the total cost of manufacturing X items is given by this function c of x. The first thing we want to do is find our average cost function. So keeping in mind the idea that any average function is the original function divided by x, this would give us 40,000 plus 200x divided by x, or we could write this as 40,000 over x plus 200. So we generate our average cost function. Then we're asked to find that average cost function evaluated at 500, which we could find to be 280. And then interpreting that result, we could say that if 500 items are being produced, then the average cost per item is $280. So evaluating our average cost function at a specific amount tells us what the average cost per item is at that particular production level. In part C, then, we're asked to find the marginal average cost function. So we would go back to our result in part A, use Wolfram alpha to generate the derivative of this function, which would give us negative 40,000 x to the negative 2. Then in part D, we'll evaluate that marginal average cost function at the exact same production level of 500, which in this case is negative 0.16, which again is something less than 0, so our interpretation will deal with something decreasing. In this case, we can say that when 500 items are produced, the average cost per item is, again, decreasing since our marginal function generated a negative result. So our average cost per item is decreasing at a rate of 16 cents per item. So in part B, we found the average cost per item. In part D, we found the rate at which that's decreasing as we produce one more item. So in part E, we're asked to use the results above to estimate the average cost per item if 501 items are being produced. So in this case, that would be 280, which is the current average cost per item, minus 0.16. So if we're going from a production level of 500 to 501, then our average cost is decreasing by approximately 16 cents. So we take that difference to generate a new average cost of $279.84. In our last example, we're given a price-demand equation and a cost function. And what we want to do in part A is find the profit function. We'll construct our marginal profit function and provide some similar interpretations that we've done with the past examples. So in this case, we're given a price-demand function in terms of x. X equals 8,000 minus 20p. So our first step would be to take that price-demand function and solve for p, which would give us 400 minus x over 20. From there, we can generate our revenue function. So revenue is always price times demand, so we would take x times our price function, to generate our revenue function. The last step then will be generating our profit function, which is revenue minus cost. Making sure to put that cost function in a set of parentheses so that we know that that subtraction or that minus gets distributed across both those terms. So subtracting those two equations from each other will give us negative x squared over 20 plus 330x minus 112,000. So we had a little bit more work on the front end to generate that profit function that we want to work with. But now we could find the marginal profit function by plugging that function into Wolfram alpha and calculating the derivative. That result would be 330 minus 1/10 x. In part C then, what we want to do is evaluate the marginal profit function at a production level of 2100 units, which would give us a result of 120, which in this case is greater than 0, so our profit function is increasing at this production level. So we could say that at a production level of 2100 units, our profit is increasing at a rate of $120 per item. So again, another way to say that would be if we increased our production by 1 unit, we would see an increase in profit of about $120.